Standard molar enthalpies, which are symbolized using this symbol right here, are kind of similar to standard molar enthalpies. The standard molar enthalpy of formation of a substance was the enthalpy change that occurred whenever a substance was formed from its elements at standard conditions, which standard conditions is 25 degrees Celsius and 1 atm. It's the same sort of thing for standard entropy. It's the entropy value of a substance at standard state. One big difference is that enthalpy formations for pure elements was 0 at standard state, but all elements will have an entropy value at standard state because all elements will have entropy at any state unless they are a pure crystal lattice at 0 degrees Celsius. Such as the third law of thermodynamics told us. Just like with enthalpies, entropies are going to be different depending on states. We already know gases tend to have greater entropies than liquids. In general, entropies tend to get larger when you have larger molar masses. There tends to be more disorder when there's more particles present. And in a similar vein, you tend to get more entropy when you get more atoms. You can use this equation here to find the entropy, the change in entropy in any kind of reaction. Notice that this is almost identical to the enthalpy equation that we saw before. Also, since there were many different ways to find enthalpy, we could use Hess's law. There are also going to be other ways to find entropy as well. So there's a lot of similarities here between entropy and enthalpy. The next thermodynamic function we're going to look at is Gibbs free energy. Gibbs free energy is abbreviated with the capital letter G. And this is our third thermodynamic function. We have entropy, enthalpy, and now we have free energy. And these three things are related using this really, really, really important equation. This equation will work if you have something occurring at constant temperature and constant pressure, which is how most of our reactions are going to be. Temperature has to be in Kelvin, and we can use this to find any of our three values for free energy, enthalpy, or entropy. One of the things that free energy is used to do is you can use free energy to predict spontaneity. For our other two, entropy and enthalpy, you can get a prediction of a tendency. Spontaneous reactions tend to have increases in entropy, but they don't have to. But Gibbs free energy, G, it tells you absolutely whether something is spontaneous or not. So, if delta G is negative, this reaction is spontaneous, and that is absolutely true all the time. If the change in free energy is 0, our reaction is at equilibrium. And if it's positive, that means that this is non-spontaneous, and you have to push it to make it happen. However, your reverse reaction is going to be spontaneous. Another way of saying this is if you have a spontaneous reaction, its free energy is decreasing, so its change in free energy is always going to be negative. Just like entropy and enthalpy had a standard entropy, standard enthalpy, there's also going to be a standard free energy. It's going to be the free energy of a substance in its standard state, 25 degrees Celsius, 1 atm. And just like with entropy and enthalpy, it's really hard to measure change in free energy directly. Instead, we measure change in free energy for an entire reaction. Another thing about free energy is you can use it to predict what direction a reaction is going to go. When you have a delta G that's really, really, really negative, that means that the reaction is going to push really hard towards the product side, toward the right. So you can kind of think of this as a way to measure the degree to which the spontaneity occurs. A really spontaneous reaction is one that has a great tendency to move towards reaction to the right. And since there's this relationship, then you can also use this to calculate K, because K is all about if our reaction goes to the right, to the left, or is in equilibrium. And we're going to see that in the next section, I think, or the section after that, the relationship between K and delta G. Just like with enthalpy and with entropy, there are multiple ways to calculate free energy. One way of doing it is by using this super duper equation right here. This equation is pretty easy to use. The only thing you have to watch out for are the units. Sometimes they'll put delta G in kilojoules per mole, and they'll have delta H in joules per mole, or they'll have it in, or they'll have the temperature in Celsius. It needs to be in Kelvin. You need to just watch the units pretty carefully when you're putting them into this equation. Other than that, these equations are pretty straightforward. So let's see some examples of this. I'm going to go ahead and skip part A for right now and try part B first. So in part B, we're going to calculate our standard entropy change. We're going to be using this equation here. If we go ahead and plug in the numbers, we get this right here. And our units all agree with one another, so we don't have to worry about that. And this is what we get for delta S. Usually delta S is shown in joules per mole Kelvin, or just joules per Kelvin. And so you may see the answer in joules per Kelvin, you may see in kilojoules per Kelvin. But since our others were in kilojoules per mole, this one is also in kilojoules per mole Kelvin. The next question is asking for a qualitative analysis of delta S. It asks if ClF3 were a liquid rather than a gas, how would the sign and magnitude of delta S be changed? Well, if you're producing a liquid instead of a gas, that means the disorder is being reduced. So that means that delta S is going to be more negative. Delta S was negative before because you had 4 moles of gas turning into 2 moles of gas, so you had the disorder decreasing some. But if you turn into a liquid, it would decrease even more, so it's going to be a greater negative number. The next question is going to be another qualitative question. Here we have Cl2 with an entropy of 222.96, and we have ClF3 with an entropy of 281.5. Whoops. So ClF3 has a larger entropy than Cl2, and number 1 here wants us to say why that is. Well, ClF3 has more atoms. It also has a larger molar mass. Because of that, since it has more atoms and more molar mass, it is going to have a greater number of microstates. Therefore, it is going to have a greater amount of entropy. And then on number 2, it wants us to calculate the value of the absolute entropy of F2 at 298 K. Remember, there's several ways you can calculate entropy, so you have to figure out what's the best way to do that. Since we've already calculated back in part B the delta S for the entire reaction, and since we now have the delta S standard for one of the products and one of the reactants, probably the best equation to use is this one here. The easiest way to remember this is remember this is true for enthalpy, this is true for free energy, and this is true for entropy. It's just the reaction equals the products minus your reactants. So when I start plugging this stuff in, the delta S that I got from my reaction in part B was in kilojoules per mole. These guys here are in joules per mole Kelvin, and so I need to make sure to change that kilojoules into joules. So I get negative 134 for the delta S of the reaction. Now I can plug in the 2 that it gave me in part D. Okay, here's my products. Don't forget the number 2, the coefficient of the balanced chemical equation. I use that for N. And here's my reactants. And my answer is going to be 158.01, and that's going to be joules per mole Kelvin.